So the question was, how do you connect the planet name strings with the result, correct? So I'll just give it with an example. I'm actually going to go and show my command history because I just did this with this other example that I think would be sufficient. So where is it? Do you see it? We did years and then the other variable. It was like trash types. Is that older?
Yeah, that's exactly.
Wasn't this years?
Yeah, because we were trying to look at that too. Yeah, we didn't really have that with them.
Oh, there we go. Okay, so let's say that you have some data and I stored it in the variable years, and then some names and I stored it in the cell array trash. So if you wanted to, I'll do this in here actually. I think that will be easier. Let's see. Because that way, because you guys did it with a loop, right? So I'm going to show it with a loop. Okay, so there's a couple options. So if you're trying to just locate, some condition, you're going to loop through all the elements, and then you have like an if statement inside, right? So let's just do the ones that are less than 300. Okay, so you have two options. One is you can write this as though it's replacing the find command, and one's as though it's replacing logicals. So if you want to do the find command, you're just going to set up an empty array and then fill it in within this condition. So anytime this is true, it's going to add that element to the array end. I think that's what you guys did, correct?
Does that work with multiple conditions though? Because that was
Yeah.
what I was getting confused.
I think your guys' were all nested if statements, right? Yep, so it'll just, anytime it gets to that spot, all of those conditions were true, so you want to save the index. Yeah, so if you had another one that years also needed to be, I don't know, it doesn't really work with this one.
End up as the second one unless the first one's true.
Right. So you don't have to do nested. Nested and ands are the same, so a lot of people just did a bunch of ands and didn't do nested if statements. So that might logically be more convincing. The other option is to create a I want it to be false. Create a array that is all zeros and then turn each one associated with that element onto true. So this would be like the equivalent to a find, and this would be equivalent to logical indexing. Once you get either of those, you can just plug either of them and they'll work the same way back into the array that's holding the strings. So either of these will do the same thing. Does that make sense? Any questions on that?
Kind of on the right track.
You didn't do this part? Oh, I thought you did do that part, but
I was trying to do logicals. After I handed it in, it was still frustrating me that I couldn't get it, so I tried to go back and do logicals and get it to work.
yeah, you have to make sure the initial array is a logical, so you either need to do like this will make it a logical. You can see here that it's logical. And then if you went in once it's a logical, if you go in and change it to a true, you can use just regular 1 or 0. But you could also just create like an array of zeros, and I think this is what I showed you in lecture, and then use the logical function to convert it into a logical, and that'll do the same thing. Yeah, people tend to either do it one way or the other, add that end on, or this. This is actually better because it, the other one you can't pre-allocate, you know, because you have to keep adding to it. So this would be a better way to do it, and this is a very small, logicals are very easy to save because they're just binary, you know, so it doesn't take up very many bits. So this would be probably the most efficient way to do it. Okay, so let's move over to topic 8. Topic 8. That's what we're on right now. So right now in the class, we're transitioning to a very different kind of section of the class, in that we are now done with doing like our basic programming topics, and now we're going to do 8, 9, 10, 11, 4 topics where we're going to apply what we've learned. And I've chosen topics that are related to engineering analysis that you should have seen before, or that you will see. So a lot of it is very math focused rather than like physics focused, because there's no physics requirement for this class. The only requirement is that the co-req of Calc 2. So that's why some of these are chosen that way. But just know that pretty much anything you do at this point in any other class, whether it's differential equations or just, you know, your basic problem sets that you're going to be doing in your other classes, they can all be done in MATLAB, and MATLAB can make them much easier for you. And so what I've tried to do in this part of the class is just kind of show you that by having you do problems like that, and to work in some tools that can help you. So one of the things that we don't cover in this class is any of the toolboxes. So when you download MATLAB, as a student it comes with all of the toolboxes. That's very expensive. As if you move on to the professional version, you have to pay for almost every toolbox. And a lot of your classes, when they use MATLAB, they just use the toolboxes. They don't, I mean, it's like half and half. If it's like a modeling or computational class, it'll use just what we've been doing, where you're using it for computations. But like, let me try to think of one. I think vibrations uses one of the toolboxes. There's like a signal processing toolbox that's used. But toolboxes they're just like already developed code that can kind of demonstrate some of the relationships that you're looking at in some of the classes, and they're almost all they have GUIs, so you're just like pushing buttons. The other big one is the Arduino toolbox is used a lot. So the only one that I'm going to be showing you is the symbolic toolbox. And that's because right now it's really useful for you because you're all taking calc usually. So the symbolic toolbox, I'm just going to show it to you on MATLAB, is an analytical toolbox to do derivatives and integrals and basic algebra, and simplifying equations, and like you can multiply through and what is that called? Expand equations and whatever. So I'll show you some of that. And that's what your pre-lab will be, for the most part. It's very similar to Mathematica, if you guys have ever used Mathematica in your calc classes. And then we are going to look at both derivatives and integrals, but in their finite formation. So we're not going to look at the continuous calculus formation of how to do those. We're going to look at how a computer can do them. This is my favorite topic. It's also the topic that is most relevant to any higher level analysis in engineering, because once you get into looking at any system that is beyond the complication of an academic setting, going to be solving that on a computer, and you're going to be solving differential equations. So let's just talk about the difference real quick. I hope this is just review. So the assumption is that you have seen everything on the right-hand side, which is all of the analysis techniques that you've learned in calc to look at some continuous function that has dependence on one or two variables. The nice thing is that when you're starting to do discrete analysis, it doesn't matter so much. A lot of the things that they break up so carefully in calc, like whether it depends on one or two variables, whether you're taking a partial or an ordinary derivative. And the analytic relationship is not possible to look at really on a computer, except for if you use the symbolic toolbox. So what the symbolic toolbox does is it's just programmed to remember that the derivative of anything is something else. So if you put in what's the derivative of x squared, it just remembers by storing it into the system through programming that the derivative is 2x. So that's what the symbolic toolbox does, but I find that this, because I'm introducing this at the same time people get these confused, that computers, remember, they cannot do calculus, they can't do derivatives, they can only turn on and off bits. And so what you have to basically do is convert calculus into something a computer can do. And so that's what discrete analysis is. And it allows you to break up a function or some data into its discrete points, and everything is going to be on a grid. And we use the I notation for the grid, so you'll see that a lot. And so we're going to learn what some of these techniques are. So this is what we're focusing on in the Topic 8 lab. Okay, so let's just show you some of the toolbox stuff. I'll just move over to MATLAB to show you this. Okay. So if you want to use the symbolic toolbox, all you have to do is first declare a variable as symbolic. So the way you do that is you type SYMS space, and then you list any variables that you want to be symbolic, and you'll notice in the workspace they'll come up with this data type SYM. What that means is that anytime you use that variable, it doesn't have a value. It's just being MATLAB just knows that you care about its relation to other things. So if I put in a function that depends only on x and then save it to another variable f, you'll see now f is also symbolic because it depends on that symbolic variable. And then there's just a bunch of functions. So this toolbox doesn't have a GUI. It all operates within the command window, which is also unusual. But there's the diff function, which takes derivatives. There's the integral function, or int function, that takes its integral. there's multiple inputs that you can add to this as well. For example, if you create a, I know you guys haven't had, most people haven't had Calc 3 when they're taking this class, but you can create functions of more than one variable. And then when you do the derivative, you're going to say, I want to take the derivative of g, this multi-d function, and then you have to tell it which way you want it. So this would be equivalent to partial g partial x. It would take the derivative with respect to the x variable. So you can add that in there. One thing that's helpful for the integral, so if I just go back to integrating the f function, you can include bounds to actually plug in what you want it to integrate to and from. And so if you ever have an analytic function and you're using it to test a discrete method, you can use this to check if you're doing the discrete analysis right, for example. But I like to show this just if it's useful for any of the classes where you're doing analytic calculus. There's also a bunch of functions, simple, simplify I think is one, and those can take and simplify algebra. There's more, like expand is one. And so if you just go into the help and look up all the MATLAB symbolic, they're all very easy and straightforward to use and to understand. But just know that they can really help, especially if you're doing a very complex problem and you want to check your answer in MATLAB. This is an option. Do you guys have any questions about that? Okay, so that's my little quick demo on the symbolic toolbox. Let's continue with just talking a little bit about the discrete versus analytical, because I really like you to think about this like philosophically before you start programming it. So remember that that calculus is a human language, right? It's a way that we have decided to describe the relationship between time and speed, right? It's something that we came up with, and it's all symbolic representations of some sort of like math. And so what we have to do is we have to convert that into something discrete that a computer can do. And so what we end up doing is, like, if you have a derivative, you probably already know this. So what's a derivative? Like, what's the derivative of distance over time? That's speed, right? And so if you were trying to calculate the speed of a trip that you were taking, and you would just look at the amount of distance you've traveled, so the difference between the distance you started at and the distance you ended at, and then divide it by the difference of the time that you started at and the time that you ended at, right? And so all a derivative is a difference. It's just a subtraction. And computers are very, very good at doing algebra. Any sort of algebraic computation they can do very quickly. They can do it in parallel, so they can do a bunch of them at one time and relate them. So a derivative becomes a difference. And then what do you learn in calculus that an integral is graphically?
The opposite.
It is the opposite, but if you have a graph of a function, yeah, it's an area under a curve. So when it comes down to it, it's actually just a sum. You're just adding up a bunch of function values, or adding up a bunch of a bunch of areas. So if you have this, you just need to break this up into a bunch of areas and sum them up, which you've probably seen before in a previous algebra or calculus class. So what you want to be able to do, what's still being done in numerical methods still now, this isn't something that's like figured out, we know how to do it the best way, is we need to take advantage of the computer's ability to do calculations really, really fast. And so you need to break down this like calculus language into differences and sums that a computer can do. And that is what numerical methods are, basically, is the communication of those two things. And when you go on to 303 from this class, this is primarily what you're going to be doing, is numerical methods. So let's look at a few of them for each. And keep in mind that for every single thing that we're going to be programming in the next 4 topics, there are already intrinsic functions that do what we're doing that we're going to use to check. And so I often get students saying, like, well, if there's an intrinsic function, why would we ever need to write our own? It's like a huge complaint that I get. But trust me, you don't want to be doing the next thing that you can do after you already know how to use the intrinsic function. Do you know what I mean? Like, it only gets harder. So like, you first need to start somewhere. And so we're going to start where we can compare our answer to something that already exists so we can get an idea of it. Don't worry, when you go into 303, you can try things that are much harder. And they will be easier once you've already done the more straightforward things. So does anyone remember the fundamental theorem of calculus? That seems like an important theorem to have remembered if you took calculus, right? Oh, it's okay.
It's just that, like, your slope has to be the same at some point over the interval, isn't it? As the slope is.
Yes, it is just that the slope is the derivative, basically, as long as the points are close enough. That is what the fundamental theorem of calculus is. So it's how they prove I don't even know what it's used for, actually. I always use it in numerical methods to show that if your mesh is fine enough, the approximation of the derivative approaches the exact derivative as long as the mesh is fine enough, whatever that means. So let's say that you have a continuous function and you have a point h and then you have another point next to it that's h. Oh, wait, sorry, did I say h? You have a point x and you have another point h away from it. So we'll call that point x plus h, and then you have the two function values. The derivative is defined according to the fundamental theorem of calculus as just the rise over run of those 2 points, as long as it is in the limit of that difference approaching 0, so the points getting closer and closer together, meaning that this is an exact approximation as long as the points are exactly the same or approaching exactly equal to each other, just like they always do with limits. So we're going to do more or less the same thing, but with discrete data. So the only reason that you would ever take a derivative using discrete data is because you don't have the analytic relationship, it's not known, or the analytic derivative isn't known. That's also a possibility that happens for math people. Usually the relationships we're using in engineering aren't that, but sometimes, like in high-level research, that happens. So let's say you had some points, and I'm going to label these points, and that's how we think about points now. We label each of them with an index, and so when we talk about them generally, we refer to them as the I point, so I'm just going to label one of them as the I. It's the third point that I've labeled. And then you just have to remember that the point next to it is going to always be referred to as I plus 1. So it doesn't matter which 2 points that you're talking about. We're mostly interested in the relationship between the points when we write these kinds of methods. So that means that the distance between the 2 points is going to be referred to as h. We can index h because sometimes the points might not be evenly spaced, and 2 neighboring points might be different distances from 2 other neighboring points. So if we wanted to approximate for this data, so again, you can just imagine that this data is something like distance and time. It's probably the most like intuitive derivative relationship that you work with. If we wanted to know what the derivative was at a single point, we would just take the difference between itself and its neighbor, and I've made a choice to use the neighbor in front of it, so I'm just taking and approximating this derivative here. I'll draw in approximately what that derivative would be, so it would be a slope, right? So it would be like connecting those 2 points. I'm going to approximate it as just rise over run with those 2 points. And as long as the points are close enough, the approximation is good. And all it does is it allows you to replace those derivatives with integrals. So that's the basics, and we're going to look at a couple different types. So the first type is called a forward derivative, and that's the one I just showed you, where it uses, to approximate a derivative at an I location, it uses the point in front of it, or the next point. So remember, we're in engineering, we're taking derivatives with space and with time. So like when we talk about them, a lot of times we're naturally just talking about them in one or the other. So a lot of times we'll use, like we wouldn't use a forward derivative in time because you wouldn't know the information in the next time step. So you'd want to use a backward derivative for time derivatives. Where for spatial derivatives, it really just depends on where you're taking the derivative. So if you're taking a derivative on a boundary point at the end of your domain, you're going to choose backward or derivative for that reason. So I'll just show you it with 3 points each time. So if this is I minus 1, this is I, and this is I plus 1, the slope will use the point in front of it. So the backward uses the point behind it. These can get easily mixed up when you're not thinking about a particular situation, but they are different because think about it as where you're taking the derivative at. So it matters whether this is I or this is I plus 1. As always, it just matters the relationship between them. So here I'm going to do the difference between the I and I minus 1 points. So on this same graph, the slope would be different. It would be a different approximation for the same point, same data, right? And then the last option is the central, and that just uses both neighboring points. And so the formula that you use for this doesn't use the point itself. So you're approximating the derivative at point I. So with the same 3 points, I plus 1, I minus 1. But the derivative doesn't use the point that you're taking the actual derivative at. It skips that point. And so the thing that happens with this formula is that this now is spanning two grid cells, right? So if this was h, this would be over 2h because your derivative is taking over the 2. So you're going to be doing this in your lab. And there is no intrinsic function for derivatives because it's just a subtraction. So they don't have a function to do that. Actually, they do. It's called diff. I think you do it in your pre-lab if you want to just take the difference between two arrays, but you can also just subtract them. So if you have some data that you're trying to differentiate, I'm going to create some from an analytic function. So I'm going to create numbers 1 through 10 and then just create function values that are the sign of that number, and I just want to take the derivative of it. To do that, you can either do it with a loop where you're just going to loop through each of those 10 points using the I-index and then just save each of them to, I'm going to call it df to be the derivative. And you want to pre-allocate this. This is the first example where you can kind of see why you need to pre-allocate. So I don't want to write the whole thing for you, but the idea is that you will write out that formula inside an I loop that just loops through each one. But you just have to think about it because you can't do a central derivative so a central derivative is the best derivative to do. It's the most accurate because it uses two pieces of information, so that's what you want to use. But you can only do that on the interior points. So all the middle points you can do that, but then on the end points you have to do something else, right? So you have to set up this loop so that it can run through and figure that out. And there's a lot of different ways to do it. So you can start the loop from 2 to the end minus 1 and then fill in the boundaries, or you could do forward derivatives on all the points except for the last, or backward derivatives on all the points except for the first. That's up to you. You can also do this using index notation, where let's just say you wanted to do forward derivatives. You could access all the points but one and then subtract off. This is like doing a lot, so if this is confusing, you don't have to do it this way. So this would just do that subtraction. It would subtract 2 from 1, 3 from 2, 4 from 3, but it would do it all in one step rather than doing it in a line. So this would be the vector equivalent of that. You guys have any questions so far about derivatives? Okay, so let's talk about the integration now. So I need to just show you some notation before I show you the formulas that you're going to use. There are intrinsic functions for all these derivatives that you can use to check your own, but you can write this code in one line. It's really not hard. I never use the intrinsic functions for simple things because I'd rather know what I was doing than have to use the black box functions. So if you're trying to integrate a function from a to b over the x domain, we just talked about how that is equivalent to the area under the curve. So when I refer to any integral in these formulas, I is the full integral. It's the full area under the curve from whatever 2 points you're trying to integrate to. And that's probably the most confusing thing about numerical integration formulas, because when you start thinking about doing this numerically, you're going to have a set of points, and I'll label each point again. So let's say you had 7 points here, and you wanted to know what the integral from the first point to the last point was over the entire domain. To do that, what you would do is you would make a rectangle to approximate each section, and you can do it a bunch of different ways. But let's just say that we used the point as the function height, and we created 7 rectangles. Okay, so you have an x location associated with each of these points as well. If you wanted to approximate this full integral, each of these rectangles would first need to be calculated, the area, and then they would have to be summed up. So when you look at integration formulas, what you're going to see is that the I is indexed, and that's because it's the integration formula for one rectangle and the area of one rectangle. And then in order to get the full one, you have to sum them up. So for example, if you're using, like, if you remember, like the left or right point rule, midpoint rule, you don't just like take the whole function and then just make it into one rectangle. That would be a horrible approximation of any function. You have to break it up into a bunch of rectangles and then sum them up. So you'll see these integration formulas as some weight times some function value, because there's like a million different ways you could approximate the area. And so the weight is, it's kind of like, it's typically the width of the rectangle, but not always, because sometimes the function values are approximated in a more sophisticated way. And typically the f value here is the height of the rectangle, or the actual value of the data. And so what I'm going to show you now are the different ways that you can approximate II. So how can you approximate this area? What are the different things? And you've probably seen or heard of most of these. So I'm going to show you three types. The most basic one you can do is the rectangular rule, where you simply approximate the area as the distance between the 2 points and one of the function values. So if this is, if it's this formula, fi, this would be the left point rule. If you used the point next to it, that would be the right-hand rule. I'm going to just draw.
Wouldn't the first one, hi times fi, wouldn't that be the midpoint?
This one?
Yeah.
Well, let me show you how these are labeled, and it might make more sense. So let me just label a few points here. I'm just going to pick out 4 points. So, and I'm just going to calculate the area at I, not any of the other points. So there would be 3 areas on these 4 points. So if I wanted to do the left-hand rule, I would just start the rectangle at the left point, and I would go over to the right point and down. I'm going to change this point to this location. So kind of overshoot compared to the right-hand rule, which would maybe undershoot the actual area that it might be. And then this would be, let's see, this would be H or II. And then the right-hand rule, I'll do in green, would be that. I actually am going to skip midpoint rule because it very much confuses people, because if you have data, which you do, that's why you're using it, the midpoint rule is very confusing, because a midpoint would say take the average. No, it doesn't mean that. The midpoint rule would mean that you need to have a point between the 2 points in order to take the area. So you would actually have to go across 2 full grid cells in order to do the midpoint rule. So the midpoint rule, I'll just show it. If you did the midpoint rule, you would have to cross 2 full cells. So you'd have to have a point in between, or it's not the midpoint. Because taking the average is something else. That's called the trapezoidal rule.
So you're kind of losing half your points.
Yeah, or you could interpolate to get the point that would be in between, but it's not really a realistic approach for data because that point doesn't exist, so why not just use an approximation that uses your points and just, yeah, so I don't know. It's like one we always learned about when we learned these, if you ever took a math class where you learned, but I find it's actually not that useful for numerics. So the one that is the easiest and the most accurate, the most accurate, but one that doesn't get too complex to program, is trapezoidal rule. And so that's the one you're going to program in your lab. So what trapezoidal rule does is it averages the 2 functions at the I location. So it's just going to take your I location function value and then the one next to it, add them and divide by 2, and then multiply by the distance. And graphically, it makes a trapezoid. You'd have to do a little bit of geometry proof to maybe convince yourself of that. But if you just like calculate the area of the triangle that's made from this, you'll see it. But if you have 2 points, like this one's I and this is I plus 1, then the trapezoidal rule will connect the 2 points. It makes a trapezoid. So it's much more accurate. It's second order accurate. We don't really talk too much about accuracy. You'll do that more in 303, but you can basically measure the accuracy of these, and it's twice as accurate as the other 2 methods, which just means that as you decrease your mesh size, it gets even closer to the exact solution compared to the other methods. Okay. So I want to be very clear about this now. So these integration formulas, they're over a single interval. These are the approximations of a single rectangle's area. So your integration that you're going to do is to take those and sum them up over all of the intervals that you use. So like if you're using left-hand rule, well, if you're using any of these, each rectangle is approximated with 2 points. So if you have 100 points, you're going to have 99 areas to integrate. So it's a sum, and so you can either write your own sum function, which you've done in lab 6, you already did that, and then just call on your sum function for this, or you can just write this into a sum function. It's up to you what you want to do. Let's see what I want to show you here. So with rectangular rule, it's a really easy sum, because all you're going to do is sum over all of them, all the points but the last point you don't need to include in the sum because there's no other point to approximate a rectangle. And then you just, it's just this, you know, so you're just going, this could just be a loop where you have like my sum equals 0 and then my sum plus h of I times f of I within a for loop that runs from 1 to 99 or 1 to n minus 1. So that's how you could do this one. You could also vectorize that as well to multiply and sum by calling a sum function. You just have to call your own sum function. Trapezoidal rule isn't quite as straightforward to vectorize, but you can. So I just wanted you to just have a chance to think about how you might do that so that you could write this in one line rather than more. So this is the formula that we just wrote out for all the intervals, right? So you're just going to take the two function values, add them, divide by 2, and multiply by the width. So if you think about this for a particular problem, so I'm just going to do 5 points so you can see it with an example. Remember, trapezoidal rule is going to take and make 4 trapezoids. And with 5 points, you can even just write it out. These are all, let's just say these are all evenly spaced by h. So I'm going to pull the h over 2 out. So for this example, I'm going to have h over 2 pulled out, and then I'm going to have 4 different things that I'm summing up. The first one is going to be f1 plus f2 times h over 2. That'll get this first one. And then you'll have f2 plus f3 plus f3 plus f4 plus f5 plus f6, right? So what do you notice? How many times is, oh yeah, f4 plus f5, thank you. So f1 and f6 are used one time. Sorry, 5. f1 and f5 are used only one time, but all of the rest of those 3 interior points are used twice. And that would be the same as 100 points or 1,000 points. The first and last points get used once, and all the interior points get used twice. So you can see the pattern, and you could easily just create the formula by recognizing the pattern. So you're going to sum all the interior points multiplied by 2, add 1, add the end, and multiply them by h over 2. You know, it's pretty easy to generalize. So you can either kind of do that, you could just write this sum out in a loop, or you can, well, if you were going to vectorize, I would vectorize with this pattern. So those are really the two options. So you guys have any questions about that one? Okay, so I'll see you in lab.